Hello everyone. Welcome back to mechanics of materials and previously we introduced the scalar formula for a moment. Okay, the scalar formula for the moment is the magnitude force times level R. Okay. So let me write this. Let me take a note of that. Where sorry. Where is my pen? Oh, yeah, here. Okay, so welcome back. Okay, last time we say scalar formula for a moment. We need the force times the lever arm. Okay, actually, this is force. This F means the magnitude of force. Magnitude of of force. And the moment will cause the rotation. Okay, so and in the scalar formula, I think the most important thing in the previous video we say it's the most important thing is to find the lever arm. The lever arm is the perpendicular distance from O is a reference point. Okay, when you're trying to calculate a moment, must be a reference point or reference axis. Yeah, it's perpendicular distance between your reference point or reference axis to the line of action of force. Okay, line of action force. And I don't want to explain line of action force. You just make an extension of your force vector and try and then find a perpendicular distance between your reference point and the line of action force. You will get your lever arm. Okay, that's for scalar formula, and especially when trying to do the planar calculation or 2D like calculation, scalar formula is enough. Okay, but in yeah, and for this section, I just introduce maybe some mechanical problem you need to calculate the moment in 3D space. Okay, and in 3D space and 3D space or 3D in 3D space, if you use the scalar formula over the moment, that doesn't work at all. Okay, and it will make the problem very difficult, calculation problem difficult, and we need another tool. Okay, and this tool we call the cross product. Okay, cross product. It just cross product it's A cross B, A vector cross B vector. And the cross product just okay, product of two vectors and become a new vectors. Okay, cross product just multiply two vectors and then become a new vectors. That's called cross product. Actually, there is another product. It's called dot product, and dot product is two vector multiply together or become a scalar. Okay, but here we just show the cross product. Cross product means two vector multiply together become new vector. Okay, okay, so it's A cross B, and there is some rule for cross product. Okay, I think the most important rule is A cross B is not equal to B cross A. Okay, and the cross product we use the right hand rule at the same time, the same thing you judge the just like we did in a rotation moment in scalar formula of the moment. Okay, it's a right hand rule. Okay, so A cross B, so we just start from A cross B means you start from the A and then use the right hand cross B. Okay, because A is here and B is here, so A cross B. So if it's hard to demonstrate in the screen. It's A cross B, A cross B, A cross B. Okay, A cross B, and then your sum is the vector, the resulting the C. Your sum is a C, A cross B vector direction. Okay, so A cross B is point up. But if you B cross A, so you will become as B start from here, B cross A. So your sum is down. Okay, that means B cross A, your vector direction is pointing down, and A cross B is pointing up. So A cross B in general is not equal to B cross A. Okay, And I think that's the most important operation rules for cross product. A cross B is not equal to B cross A. And that tell you the order of the cross product cannot reverse. It will generate different results. But on the other hand, if we're doing a dot product, A dot B equal to B dot A, that's no problem. But for the cross product, A cross B is not equal to B cross A. Okay, so here is one sentence from the textbook. Proper order of the cross product must be maintained since they are not commutative. Okay, that means your order the sequence A B is not equal to B A. Okay, so so what's the so when do the cross product calculation, what's the result for for a cross product? Suppose we have a vector and b vector, and we represent these two vector by Cartesian coordinate, or let's say expressed as a Cartesian vector. Okay, this is a Cartesian vector of axi plus ay plus azk, and ax, ay, az are component. Okay, ijk is the unit vector of x-axis, y-axis, and z-axis. And b, yes, the bx, by, bz are component of the b vector. Okay, in x-axis, y-axis, and z-axis. Okay, so what's the result of A cross B if we use the Cartesian vector formulation? Just very simply, very simple. Just put this product, two cross product together and doing the multiplication. And after all, you can summarize this cross product as this very simplified determinant. And why is that? Okay, let's start from very beginning. Okay, like I said, A cross B, just put these two vectors in the cross product. What does that mean? Okay, I see the screen. Okay, I see the screen. Can I move the direction? Looks like can I move? Okay, let's see here. Okay, yeah, we have two vectors when we're doing a cross product together. Yeah, sorry, I forgot this cross product. Okay, cross here product. Okay, A cross B. Okay, A cross B. A cross B. Okay, so it's just the multiplication ax times bx, ax times by, and ax times bz. Because ax, ay, az, bx, by, and bz is just the constant. Just multiply the constant. Okay, nothing else. So it's a distribution law. Ax times bx, ax times by, ax times bz. And the other term is ay times bx, ay times by, ay times bz, and az times bx, az times by, az times bz. Okay, that's for component multiplication. Okay, and next thing is we have to mention is okay. Right now we just multiply the constant. Okay, but it's cross product. Okay, vector doing the cross product. Okay, component does not doing the cross product, and vector doing the cross product. So here is I cross I cross I, and here is I cross J, I cross J. Okay, the next one is I cross K. I cross K. Similar situation. Serranius. Okay, J cross I. J cross I, J cross J, and J cross K. And final one is K cross I, K cross J, and K cross K, K cross K. Okay, so what's the result of this I cross blah blah blah, J cross blah blah? What's the cross product between these unit vectors? So and there's a simple I J. Okay, simple and a simple rule, right? Okay, simple rule. Okay, so if this is this direction, okay, it's positive, and if it's this direction, it's negative. Okay, so let's check. Okay, let's check. Okay, well, how was the result will be? Okay, first of all, is I cross I will become cross product when the vector cross itself. I cross I cross J cross J, and K cross K. The vector itself cross itself is all equal to 0. Okay, they're all equal to 0. Okay, a vector cross itself will become a 0. Okay, so that's also another rule. Okay, the vector cross itself is become a 0. Okay, so so we will see that the first term this is I cross I vector cross itself. Okay, this is 0. Okay, this is 0 and this is 0. Okay, and so then next we will see I cross J, I cross J, I cross J here. So it's equal to K, okay? And I cross K, I cross K, I cross K because it's the green direction. Green direction means negative, and I cross K equal to J, and it's minus. So this is minus J. Okay, then I cross J is positive K. So, and then what is J cross I? J cross I is green direction. J cross I is green direction, so it's negative. So it is also negative K, negative K. And J cross K, J cross K is the red direction, and it's positive. So it's I. And K cross I is red direction and positive, and will become a J. And the K cross J will be K cross is green direction negative, and it will equal to I, so minus I. So after all, the cross product, what's the result? Okay, we can just write the result. The result, we just split it. I just split it. Okay, I call it I, and I intentionally put the J minus J here. Okay, and the K here. Okay, it's plus. Okay, so let's collect the I with I. The term with I first. Term with I here. Where is I? So it's AYBZ. So here is AYBZ minus AZBY. Yeah. Okay. And we collected, we have a J. So AXBZ, AXBZ, I think minus J, we have minus AZBX. And then K, final K, we return with a K, X, B, Y, my K minus A, Y, B, X. Okay. Okay, okay, what happened? Okay, so so with this, the A cross B, if we represent A as a Cartesian vector, B as Cartesian vector, we will get this result. Okay, and this result, as you see, it is very hard to remember. Okay, very hard to remember. Okay, but very lucky, very lucky. In A cross B, someone found the rule for this. A cross B, we can write in a very condensed form. Okay, IJK, right? And we just write, okay, that's the first rule is IJK, the unit vector of x-axis, y-axis, i-axis, and z-axis. And the second rule is AX, AY, AZ. And the third rule is a BX, BY, BZ. Yeah, if we're writing A cross B, you must write the A vector first and B vector second. If you want to, if you want to A cross B, okay. But if you want to calculate B cross A, so you have to write the B vector first and A vector second. Okay, right now it's A cross B, so write the A first and second B. Okay, and it's called 3x3 matrix and determinant. Determinant is called 行列式值啊。Okay, if we want to know Chinese 行列式值。Okay, and 3x3 determinant can be do the expansion, can be expansion by the cofactor using the cofactor expansion, and then doing this expansion. Okay, you can after that you can get the same result like this. Okay, so I have this in my PowerPoint. I have do the cofactor expansion. Okay, we return to this slide. Okay, okay. Here is the cofactor expansion. Okay, cofactor expansion like just like this. We just how to do like cofactor expansion. There is also some rule for the cofactor expansion. Okay, so what's the rule? Okay, let's see it. A cofactor expansion, like we can choose these three as a cofactor. Okay, we choose these three because it's much easier to do. Okay, choose these three as a cofactor, and it's plus minus plus. Okay, so we choose this I cofactor here, so we just write I here, and then we block this, and we block this element. Okay, block this element based on this position. Okay, so you will see a y a z b x b z, and then it's a determinant. Okay, okay, so let's finish the first cofactor expansion. Okay, what's the next? Okay, the next is, okay, here we use the same here. We choose the j as the cofactor. We choose the j as the cofactor. Okay, but here we have minus sign here, so you have to write the minus j. Okay, and then block this element in this way. So you will ax az bx bz, and then write the indeterminate. And the second cofactor, the expansion, and then final the cofactor expansion. Okay, just get rid of this. Okay, final we choose the k. Final we choose the k. Okay, we choose k. So we write a k here, and here k is positive, so just write a plus k and a. And then we block this element. Block this element. It will be equal x, a, y, b, x. Ah, sorry, there is a typo. There is a typo in this slide. Ah, this should be y. This should be y. This should be y. Right. Okay, so A is Y B Y. Yeah, there's some typo here. Okay, let me check. A Y A Z B Y B Z. Okay,不大可 A X B X A Z B Z. Okay, and final A X B A X B X. Sorry, B X. Oh, is this here? It should be this one. This should be wrong. B Y. Okay, A Y B Y X. Okay. So you block this element, you will have x, a, y, b, x, b, y, and this will become 2 by 2 determinant. 2 by 2 determinant. 2 by 2 determinant is very easy to calculation. It's equal. I write the example here. Okay, 2 by 2 determinant is called 2 by 2 determinant. Okay, so 2 by 2 determinant, so it will become like AD BC. Okay, this plus is minus, also a very simple rule for determinant calculation, AD minus BC. So you will just expand this, just do the calculation 2 by 2 determinant, and then you will get the same result as this very complicated formula. Here, you'll get the same result of this very complicated formula. Okay, so that's the cross product calculation. I hope you can start to get familiar with it, because in 3D space calculation, the moment is equal to r cross f. R cross f, yeah, it's a cross product. Moment in 3D space is cross product, and then yeah, this is a position vector, and you have position x component, y component, z component of the position vector, and then you have x component, y component, z component of your force vector, and then doing cross product, and then you can get your moment, you get the x component, y component, z component of your of the moment vector. So Okay, I just stop the video here. Okay, okay. Yeah, I don't think we'll talk about this later because this video is kind of too long. Okay, I'll talk about a moment later, and then we'll see you in the next video. Okay, because I don't want to make the video too long. Okay, see you in the next video. Bye bye.